Hello everyone, welcome to this lecture. Today I'm going to talk about continuous time unit step and continuous time unit impulses. I'm Touri. I'm with the Electrical Engineering Department at UCSD. Okay, so let's begin with the definition of continuous time unit step. Continuous time unit step is a signal that is 0 for negative time and is 1 for positive time, including 0. At some places, we don't really mind what's the value of the unit step at t equals to 0. But yeah, so this is the definition that we're going to stick with in this course. So as an example, one can think about what is the plot of summation of ut minus k's, where k ranges from 0 to infinity. And if you do it, you would see that it would be u of, if this is t equals to 0, then this is going to be u of t minus 1 plus u of t minus 2, and so on and so forth. So it's really going to be a step staircase to infinity. Okay, so for the continuous time unit impulse, we need a more complicated identity, and that is actually what is introduced by a prominent physicist, Dirac, who actually invented this thing. And it has very important physical applications to the physical sciences, especially engineering. And after a while, mathematicians could make sense of it using different techniques, including measure theory and distribution theory, functional analysis. Dirac himself got Nobel Prize, and he was one of the prominent physicists of the last century. And the unit impulse in continuous time that's why it's called the Dirac's delta function. So we use this delta to denote this function, this signal. So delta of t, the unit impulse in continuous time, we define it to be a signal that is 0 for any non-zero time t, and it is infinity at time 0, such that this whole integral of delta becomes 1, from negative infinity to infinity. So basically it's a signal that is 0 everywhere except at 0, and at 0 it has a unit mass, so such that if you do the integration, you would get 1 out. And the third property is that all the rules of calculus applies to it. It's very important. So you can do like change of variable, you can do u sub, you can do all these things using it. You can do like derivative and chain rules. All the rules still apply. As a particular implication of the rule A and B, since delta is 0 or any non-zero time, still the integral from t1 to t2 of delta should be 1 for negative t1 and positive t2. So any interval that actually contains 0, if you do the integration of delta, you should get 1. In particular, if I let t1 to be negative infinity, what we get, and t2 to be some arbitrary t, what we get is that the integral of negative infinity to t of delta tau d tau would be the unit step. Why is that so? Because if t is less than 0, then we are integrating a 0 signal, and therefore it's 0. And if t is positive, then we are in this situation that t1 is negative and t is positive, so the integral is 1. So the way that we represent delta is using an arrow because it has infinite weight at 0, we use arrow. And the height of the arrow is actually the integration of that delta. So 2 times delta t, we would denote it by an arrow with height of 2. 3 times delta t, we denote it by an arrow at 0 and height of 3. 2 times delta t minus 1, it would be an arrow at t equals to 1 with height of 2. So how to make sense of such a function, such a signal, is through looking at the limit of these very short impulses. So let's define delta delta of t for capital delta. So capital delta is a parameter. And we define it to be, this delta delta t to be 1 over capital delta when t is between 0 and delta, and its height to be 1 over delta, and elsewhere it is 0. As you can see, the integral of this delta delta is just the height of this narrow pulse times its width. The height is 1 over delta, the width is delta, so the whole area is going to be 1. So no matter how small this delta is, this integral is going to be 1. And as we let delta, capital delta, go to 0, we will have a delta. So actually we view delta t as the limit of these delta deltas when the delta goes to 0. Similar to the discrete time setting, the most important property of delta is the so-called sampling property. And what it says is that if xt is a continuous function at tau, continuous signal at tau, then xt times delta t minus tau would be equal to x tau delta t minus tau. In other words, if I have a delta that is located at tau, and I'm multiplying it by another signal, it's going to take the value of the signal at tau and then multiply it by that delta located at tau. So as an example, consider a signal, the signal xt equals delta t minus 1 plus delta t plus 1 times t squared, and let's plot zt to be the integral, the indefinite integral of x tau. By the sampling property, x of t would be equal to, so we just distribute t squared among the two terms, and by the sampling property we are multiplying a signal and a delta, so located at negative at 1. So this would be equal to the value of the signal that is multiplied by delta at t equals to 1 times delta t minus 1. And the value of this signal at t equals to 1 is 1, so it's delta t minus 1 plus the value of the second signal, which is t squared, the same as the first signal, at where this delta t plus 1 is located at, which is t equals negative 1. So it's going to be negative 1 squared times delta t plus 1. And now if I do the integration from negative infinity to t of x of tau d tau, we have the integration from negative infinity to t of delta t minus delta tau minus 1 plus delta tau plus 1 tau. And that's helpful to think of this signal. So we have two deltas. This is t equals to 0, and we have two delta, one at t equals to 1, the other one at t equals to negative 1. When we are integrating, as we showed in the previous slide, we get ut minus 1 plus ut plus 1. Another property of delta is so-called shifting property, and that is when we integrate xt delta t minus tau over all the t's. And the other property that is important is the representation property, which is very similar to the discrete time case, where you can represent a discrete time signal by a bunch of summation of the delta functions at different locations. Here in the continuous time, the summation turns into integral. And the way to show this is using the sampling property. X tau delta t minus tau is equal to xt delta t minus tau. Now if I integrate both sides by tau over tau, then we have the integral of x tau delta t minus tau d tau would be equal to the integral of xt delta t minus tau d tau. And xt is now just in the independent of tau, so we can take it out, and then it becomes xt integral of delta t minus tau. And delta t minus tau is a delta located at tau at t, so therefore its integral is going to be 1, so the whole thing is going to be xt. And this is what representation property is about. This was our discussion on continuous time unit impulse and unit step. Thank you for watching.